Good morning, 12. In this video, I'm going to do questions 5, 7 and 10 from the school exam. So that's this one on a geometry problem with some iterative methods, and then question 7, which is an integration by parts question and a differentiation question, and then lastly question 10, which was this one about partial fractions and the remainder and factor theorems. Okay, so probably the messiest question here is question 5. We've got a diagram showing a sector of a circle with centre O and radius R, and the angle in here is alpha, and alpha is in the first quadrant, and we know that this point N gives us a right angle triangle. We're told that the area of the triangle ONB is half the area of the sector OAB. So straight away we can see where this is going. We're going to have to do something with the areas of the two shapes. And we have to show that alpha satisfies this equation here. So if something satisfies an equation, it means that this value makes this equation true. So what we're looking for is getting to being able to say sine of 2 alpha is equal to alpha. So let's get on with some year 10 trig. We're going to look at the right angle triangle first, and we can say that BN, I'll just get a new page working. So here's my badly drawn triangle. Here's alpha. So BN over R is equal to sine alpha, and ON over R is equal to cosine of alpha. And the area of that shape is equal to half the base times the height. So it's half of ON times BN, which is equal to half of R sine alpha, R cos alpha. So that's switching BN and ON, but that's okay. So that gives me a half R squared sine alpha cos alpha. And we know that sine 2 theta is 2 sine theta cos theta. So this is equal to a half times 2 sine alpha cos alpha, forcing in the 2, and that's times r squared. So that gives me r squared over 4 times sine of 2 alpha. And that's the hard bit done. Now let's look at the area of the sector. Well, that's probably the worst sector. I'll just not draw the sector picture. Okay, so area sector. There's a direct application of the formula, so area is equal to half r squared, and instead of theta, we've got alpha. And we know that the triangle area is equal to half the sector area. So r squared on 4 sine 2 alpha is equal to a half times a half r squared alpha. Dividing lots of things through, so r squared and 4, we get to sine 2 alpha is equal to alpha. Therefore, alpha satisfies x equals sine 2x. So that's the first part of that one done. Right, now let's look at what we had to do next. Oh yeah, so we have to draw the graph, a suitable pair of graphs. So the suitable pair of graphs here means draw this and draw this. So we're going to have one line that's going, well, we end up with this here. But that is a totally inadequate answer to this question, right? So we need to have some values put on, and we need to be kind of a little bit careful about where we draw things. So I'm going to do it properly with a ruler. I'm trying to show you what I would think about if I were the one sitting in the exam. So we'll try to draw some nice axes. There we go. And I don't have to draw the sine curve for, miles and miles. We're only interested in the first quadrant. Remember, though, that we're drawing sine 2x, not sine x. So it's going to go like this. Draw it first and then mark on your key point. So this key point here is not pi, but it's pi on 2. And that maximum is at pi on 4. And I want to draw against that the graph of y equals x. And so it's nice to be able to think, well, where would I want to be? So what's pi on 4? Well, pi on 4 is going to be it's going to be a little bit under 0.8, right? So this point here, think in ugly decimals, 1.57. So when we're out here, the graph of y equals x is not going to go all the way up here. It's going to be, you're going roughly through there. Okay, so I would do this. And I saw some really nice graphs of this in the exam, so well done. Whoosh, there's my line there. I need to label both of them. So y equals x, y equals sine 2x. And I might just pop a point on there saying that's pi on 4. I don't have to do that. But what I'm going to do is I'm going to put a big blob saying here is the only intersection or root in the interval 0 ion 2. Okay, so obviously there's another one back here, but that's not what we were asked about. So there you go, that's the second part of that question. And now for the totally boring bit, use the iterative formula, blah, 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 blah. And we have to find alpha correct to 2 decimal places. Now this one did take a little bit longer than some of them. So we just start as usual, do a wee table, here's xn, and our updating formula is xn plus 1 is equal to sine of 2xn. So let's start with 1. So then sine of 2 is equal to 0.9093. That gives me 0.9093 here. So sine of 1.18186 is equal to 0.9695. So you want to show that you're using that formula a couple of times, but after that, it's fine just to do your updating in a table like this. And what we're looking for is we want convergence to 2 decimal places. And you can see we're still bouncing around quite a bit. So we've got 0.9418 and then 0.9514. So it definitely looks like we're converging on that, but we need to show that we're there. So let's keep going, 0.9453. So both of these are converging to 2dp. So you probably could stop here, but I just would like to do one more. So I'm going to go 0.9453. And if I put in sine of 2 times 0.9453, we get out 0.9492. So we've now got, starting to get finished, and we can say that alpha is equal to 0.9522 dp. Okay, so that's that part done. Right, and that's the whole of question 5 finished off. Okay, just make sure that you're really careful with looking at what you're asked for how many decimal places you go to. Sometimes you'll be told to show the results of each iteration to 4 or 5 decimal places. You should be doing that even if you're not told to do that. But just as usual with Cambridge, follow the instructions carefully or you will chuck away marks. So on to a much more fun question, which is this one here. We've got a curve and it's a classic A-level one. We have to find the x-coordinate of m, the maximum point on the curve. And then we have to find the area of the shaded region enclosed by the curve, the x-axis, and the line x equals 1. So here's 1 here. And our answer has to be in terms of E. All right, so I know we've done this one in class, but I also know that some of you wanted to go through it a few more times. So first of all, the finding the maximum point. So this was a straightforward product rule question. dy by dx, we get 2x times e to the negative 1/2 x plus negative 1/2 e to the negative 1/2 x times x squared. And we need that to be equal 0. We know at point M it's equal to 0. The gradient is 0 there. So I'm going to factorise the e to the negative 1/2 x out straight away. So e to the negative 1/2 x times 2x here minus 1/2 x squared is equal to 0. And now I'm going to factorise out this. And of course you could do that in one step. So we've got 2 minus 1/2 x is equal to 0. So we know that at m we've got x is greater than 0. So we're solving 2 minus 1/2 x is equal to 0. And e to the negative 1/2 x is always greater than 0. So we can't have, that's why we can't have this one being the solution. This is giving us a minimum. So that gives me x is equal to 4. Now let's just check in the question with what we were asked for. Where's question 7 gone? Oh, we just had to find the x coordinate. That's all there was to it. We didn't have to substitute it back in. Right, and then the next one we have to integrate. And that's going to be a double up integration by parts. And this is it here. Right, so this is one, it's a classic one where we're going to get to differentiate this eventually, and we're going to have to do it twice over. We're doing that because this is very easy to integrate, and this one's going to have the power come down as we work through it. So we'll leave this, integrate this, and then diff this, and then integrate this. So we get x squared times negative 2 e to the negative half x at 0 and 1 minus the integral of 2x differentiating times negative 2 e to the negative half x dx. Now the easiest place to muck these up is with sign errors, so we're going to avoid that. We're going to clean everything up first. So negative 2x squared e to the negative half x evaluated here. Right, and now be really careful. I've got a negative 4 here, but I've got a negative here. Take the constant out the front. And we have x e to the negative half x dx. Right, let's evaluate this now. Simplify that a little bit. So we've got negative 2x squared, which is 1 times e to the negative a half, minus, and in here, because of the x squared, I've got 0, plus 4, and we do it all again. So we're going to leave this, integrate this, diff this, integrate this. X times negative 2 e to the negative a half x between 1 and 0 minus this differentiates to 1. So that's now just going to be the integral of e to the negative half x. So this gives me negative 2 e to the negative a half plus 4 times negative 2 e to the negative a half minus 0. And cleaning this up, I've got plus 8 times the integral of 1 to 0 e to the negative a half x dx. That gives me negative 2 e to the negative a half minus 8 e to the negative a half plus 8 times this last integral, negative 2 e to the negative a half x. And we've been so lucky with getting rid of that lower limit that we have to make sure we don't muck this one up at the very end. So here we've got negative 10 over root e minus 16 times e to the negative a half minus negative 2 times e to the 0. Hang on, I've mucked that up now, haven't I? Right, let's just be careful with this 8 and the 2. So we've got minus 16 for the top one. And then we've got minus 16 e to the 0 for the bottom one. So that's negative 10 over root e minus 16 over root e plus 16, which gives us negative 26 e to the negative a half plus 16. Actually, it's nicer to write it as over root e, I think. So you can see that when I was doing that, I was pretty hesitant about the sign. So once you've finished that, it is well worth going back and just going, hang on, have I done this bit here right? Right, so I've got the negative 16 here times that first one, and then I'm going to have the plus 16 when I'm subtracting the lower limit. Okay, very, very fiddly. Now, I've only got through two questions in this video. Sorry about that. I will be back after I've taken the dog for a walk, hopefully, to do the rest of the paper. Thanks for watching.